I would like to just explain a few things, mainly to test the connection, but also as an introduction to the course which I will give. My course is about analytic number theory, and mainly it will be about the Riemann zeta function. I coordinated with Francesco Papalardi last week. We were together in Ho Chi Minh City, and he will give his two courses the week before me on more elementary number theory. But for me, it will be analytic number theory. So in particular, I will use analytic tools, including infinite products. And so this is the kind of background that I expect from the students. Just today, just to give an example and to see whether it is suitable that I use my Blackboard, I would like to give some small talk about something which is in this book. So it's here. So this book is proofs from the book. So this is something which is edited by Martin Egner and Günther Ziegler with Springer Verlag. Proofs from the book comes from Erdős, Paul Erdős, who said that there are some proofs which are so nice that they have to be written in some book which is a reference to the Bible, even if Erdős was agnostic. And so in this book, there are many interesting things. In particular, there is a section which is on the Riemann zeta function, but it is in the chapter which is 3 times pi square over 6. And so what is the title of this section is 3 times pi square over 6. In this section, there is a result, a proof by Donzaguier, which is a proof of the fact so pi square over 6, by the way, is zeta of 2. And zeta of 2 is the sum of 1 over n squared. And this is the kind of object that we will study during the course. And Donzaguier has a very nice proof, which is included in this book, in this section, which is a proof of the fact that 5 zeta of 4 is equal to 2 zeta of 2 squared. Since we know zeta of 2 equal pi square over 6, we deduce the value of zeta of 4, and it is the same as to say that zeta of 4 is pi to the 4 divided by 90. And these are just special cases of the result of Euler. Euler proved a number of results in this direction, and I will survey this result, but I would like to give the sketch of the proof by Donzaguier of this result, which is here. And then I will make some comment on this proof. So the proof is runs as follows. You introduce the function of 2 variables, mn, and the variables are greater than or equal to 1. And this function, f of mn, is 2 divided by m cube n plus 1 over m square plus 2 over m to the cube. Maybe I will try to put some light and you will tell me whether it's better with some light. Is it better?
I think it is better before the light.
Before. So I switch off.
Yeah.
Okay.
Yeah. We can see more clearly.
It's better like this. Okay, so good. So sometimes with the light it is blinking. So
Yes, correct. That's blinky.
okay, so we introduce this function, f of mn, function of two variables m and n. And there is a claim, which I will explain after that. And once we know the claim, then the rest of the proof is quite easy. And the claim, which I denote by the star, is that f of mn minus f of m plus n minus f of m plus n, all this is equal to 2 divided by m squared n squared. Is it okay like this? Not too much on the right? No.
Yes.
Okay.
We still see clearly.
Okay. So this is a claim. I will explain you how to check this, but I will start by taking it for granted. So I use this statement together with the definition of f of mn, and then I complete the proof that 5 zeta of 4 is 2 zeta of 2 squared. And it goes as follows. We start from this claim, and we take the sum for all m greater than 1 and n greater than 1. And we look what it is. So let me write it here. So the aim, the goal is this formula here. So we take the sum for m greater than or equal to 1, m greater than or equal to 1 of the left-hand side, what is written here. So f of mn. And this first sum, we split it in 3 parts. The first part is the sum for m equal n. And so we take the sum for m equal n of what is written here. Then we have the sum for m greater than n, and then the sum for n greater than n, of f of mn. And we investigate, we look at what we get. What is the sum for m equal n? We replace m by n here, so we have m to the 4, m to the 4, m to the 4, and we have it 5 times. So this is 5, the sum of one of n4, which is zeta of 4. Now, okay, so this was f of mn, f. If you look at the sum for m greater than n, it is the same as the sum of the elements which are here. So this sum and this sum just are the same, and there is a minus sign. So this and this cancel. This and this cancel. And so if we take the sum of the left-hand side, we find that 5 zeta of 4 is equal to the sum for m and n of 2 divided by n squared n squared. But this is the product of two sums. One is the sum of 1 over m squared, the other the sum of 1 over n squared. So this is just 2 zeta of 2 squared. And this is the claim that I wanted to check. 5 zeta of 4 is 2 zeta of 2 squared. Okay, now how do we check the claim which is here? I can tell you how to do it because it's not too difficult. You have m plus n here, and you replace m by m plus n. So you will have m plus n cubed because of this one. So what you do is that you compute m plus n cubed multiplied by the different numbers which are here. So you multiply by f of mn, you multiply by f of m plus n by f of m n plus n, and also by 2 divided by n squared, n squared. So you have 4 computations to make. And what will you find for each of them? You see that f of mn is homogeneous of degree -4 in m and n. That is, the denominator is a power which is with an exponent 4. And the same here. So all this is, well, the quantity which is here is homogeneous of degree -4. We multiply by something which is homogeneous of degree 3. So we get something which is homogeneous of degree -1. And it will be a sum of some quantities, which I write here. For each of them, we have a sum of 1 over n, and we have n square of, n over n squared, m over n squared. But then we have also some cubes. We have m cubed and n squared, and n square, and n cubed. So each of these 4 quantities is a linear combination of these 6 quantities. So you write them and you check that this formula is correct. So this is the end of the proof of Zagier. I would like to make some comments about this proof. This is a kind of proof which is in this book, on the proofs from the book. And this is really the kind of mathematics that Erdős liked. And this is well suited that this proof is included in this book. Now, it is a kind of proof where we have many examples in this theory. For example, there is a result which is due to Apéry, which is the fact that zeta of 3 is an irrational number. And the proof is very clever, but it's a little bit tricky, a little bit like the one which is here. There is some similarity. Now, there are some other proofs in mathematics which are not at all like this, because it's natural to ask, why do we consider that, and how to find that we can check it, but why is this true? And this is a kind of miracle, and I will rather give a preference to some mathematics which come in a way which is easier to explain. We have some strategy, and then we apply the strategy to prove some results. And this is more the emphasis which I will give in the course, which I will give on analytic number theory on the Riemann zeta function. So this was just what I wanted to give as an introduction.
Thank you.
Okay, so thank you. I think it was useful that we had this rehearsal